Hello, welcome to our last session of the conference. And I'd like to thank those of you in Europe for sticking with us. And I'd like to introduce our next session, our lightning talk, experiences with cross-platform portability of NWChemEx using SYCL on Exascale supercomputers by Abhishek Bhagusheti. Bhagusheti, you have the control.
Thank you, Shri. Well, I'm Abhishek from Argonne Leadership Computing Facility. This next few minutes, I'll try to be as efficient as possible just to move out of your way for the last day of the Dev Summit. As the title says, I'll talk about the experiences of porting NWChemEx, which is a DOE app, using SYCL on Exascale machines. So the rough agenda for the next few minutes is brief overview about heterogeneous node architectures, what is NWChemEx. I'll briefly talk about a case study, what are the challenges that we have come across, and some brief conclusions. So talking about the Exascale machines, these are the 5 machines that we have in the DOE facility. As you can clearly see from the GPUs, we have all 3 GPUs from various vendors, Intel, AMD, and NVIDIA. So the question comes, how do we maintain our software for long term, which gives us portability and performance at the same time? As you can see from the GPU programming models, there are vendor-specific programming models listed here, such as CUDA and HIP, but SYCL is being listed everywhere. This is because it is portable to any GPU. So, and this is the node architecture diagram for the 3 machines, Frontier, Aurora, and Polaris in the DOE facility. So I've just listed only 3, just to show how complex the node architecture is, what are the GPUs and the interconnectivity between them. And as you can see from one of these 2 examples, that AMD can partition their GPUs and make it as virtual. So on Frontier, even though there are 4 MI250X, they are listed as 8 virtual GPUs. The same story goes with Aurora. Even though there are 6 physical Intel data center GPU Max series, or fondly called as PBCs or Ponte-Vecchios, we use them as 12 virtual GPUs. And this brings its whole caveat of how do we manage, how do we program, and so on and so forth. Talking about SYCL, the first question is, what are the compilers available? That's the important question. So these are the 3 notable compilers in the field, and for the rest of the few minutes, I'll briefly talk about my experiences with Intel's DPC++ implementation of SYCL standard. And even though we have used Compute CPP and Adaptive CPP, and it's a bit rather outdated that Compute CPP and DPC++ are pretty much the same. NWChemEx, talking about the application here, it is a high-performance computational chemistry code. This is just a quick overview about 30,000 feet. This has several science capabilities, all within the computational chemistry or quantum chemistry framework. As I've listed here, a few machines that we regularly test on these days, with programming models listed here. There's some key notable features of NWChemEx app is mostly used for studying catalytic reactions, biomass conversion, and the team is spread across different facilities and throughout US. So it's primarily written in advanced modern C++ standards, and the GPU programming models ranges from native vendor-based to a portable programming model such as SYCL as well. So coming to the case study and how our experiences with SYCL are, we have a specific science case, which is CCSD. This is nothing but a gold standard computational chemistry method. Again, to make things very simple, we just have one equation where we compute 2 entities. One entity is CCSD. This is nothing but a really compute expensive calculation of tensor contractions. So these tensor contractions are decomposed into several gems. So we talk about gems, which are nothing but matrix multiplications. So since we have gems, we could very easily use vendor APIs, vendor math-based APIs to get these computations done. On the right-hand side, we have another term called triples. This is the most computationally expensive part of the entire calculation, of the entire science case. So we have the single kernel written in about like 3,000 lines, very well optimized by the vendors themselves. So the NVIDIA, Intel, and AMD engineers, they did their own optimizations for this single kernel. And what it contains is there are about 27 tensor contractions fused together into a single kernel. And since it's a single kernel with such a huge density, we have high pressure, high register pressure as a limitation. So this is just a quick overview about what happens in each one of these two terms. And for the next few slides, I will talk about how do we use SYCL in computing each one of them. Talking about CCSD, the term on the left-hand side, since I was talking about gems, we use cuBLAS APIs. I don't know if this is legible. We just use several APIs from a math library, cuBLAS, dot, gem, gemv. So these are the APIs that we use from vendor-based math libraries. And not to forget, we need to specialize for the data types as well, doubles and complex types, reals and complex types. Moving forward, the story is not so different with HIP or AMD machines. So we do have the same set of APIs from ROCBLAS. Coming to the SYCL backend for Intel GPUs to start with, we have APIs from oneMKL, and there are a couple of good things about it. One is we don't have to specialize for each data type, unlike we have done in cuBLAS and ROCBLAS. So these are templated APIs, so one less thing to worry about. Second is we have written this for SYCL backend, mainly targeting Intel GPUs for ALCF Aurora. But as the specifications evolved and the portability matured, the same set of APIs can run on NVIDIA and AMD architectures without any changes to the code. So what is oneMKL? This is, again, a brief overview. You might have seen this elsewhere. This is one math kernel library from UXL Foundation. So the specifications are being maintained by UXL Foundation. The two features of this project are portability and performance. So it provides a vendor-neutral path to math acceleration. So in other words, you can use the same APIs to target GPUs from various vendors, and as well as the CPUs, not to forget CPUs. And I was talking about performance. So since these APIs are just lightweight wrappers on the vendor APIs, you will get exactly the same performance or almost the same performance as the vendor APIs. So these two are quite important in terms of maintaining huge code bases. And I show a quick table here where you have a oneMKL interface and the inner workings of it. So you have oneMKL interfaces, which just provides the APIs. And underneath it, you have a selector, which just takes the decision of whether it is a CPU or a GPU. And once that is done, you have different APIs from vendor-specific libraries. It could be cuBLAS, cuSolver, and similarly for the AMD. So this is just a simple workflow of how this lightweight wrappers gives you portability and performance at the same time. So talking about the CCSD contributions, again, I'm reiterating that these are tensor contractions, breaking down as matrix multiplications. We use the same set of APIs to get both the performance and portability at the same time. Moving to the triples component, which is the significantly expensive part. These are handwritten kernels. And I'm reiterating that these are kernels of about 3,000 lines. What we have here is these are first written in CUDA naturally, and these were ported to HIP and SYCL as we have new hardware vendors in the space. So these are some of the specific set of features, not so exotic, but these are very common set of features that we use in each programming model. And some of the SYCL specifications are outdated or removed. So this needs to be updated. The question comes, what are the challenges? Since we are developing for such a diverse set of machines with new set of compilers and tools, the immediate question comes to what are the tools that we have for debugging? And once we have the debugging, what are the tools we have for profiling? Since SYCL is portable, you have the code gen underneath providing vendor-specific instructions. The existing debuggers came to our rescue. So we could use CUDA GDB, ROC GDB, or oneAPI GDB to target the same SYCL application on these vendor-specific platforms. So debugging was never been a big problem for us. And there are some nice tools which are not so well known. These are SYCL tracing tools from DPC++ implementation. So we can use that to get some simple traces without using these vendor-specific tools as well. So there are a certain set of tools that are already mature when it comes to debugging these complex applications. The story is not so different with the profiling as well. We could use all sort of the well-known profilers such as NVIDIA Nsight System, ROCm OmniPerf, and Intel VTune similarly. And to make things a bit more complicated, when we have an MPI program, when we target these big machines for several thousands of nodes, MPI always plays a critical role. So MPI adds hodgepodge into the mix. So the next set of challenges when we were developing NWChemEx is the specialized hardware. So all these machines that I've just listed, these comes with specialized hardware called as tensor cores, matrix cores, or matrix engines in whichever vendor platform that you could choose. The question is, how do we program for these specialized hardware? Every vendor comes up with their own set of rules and restrictions. And most notably, these are like, what are the specific tile sizes for the matrix operations that you could run? What is the data layout for the matrices? And what are the data types that are supported for these hardware? So these are really the hit list, I would say, when it comes to programming for these specialized hardware on these GPUs. And programming these is rather cumbersome because everyone comes with because the instructions are rather written in assembly language. So currently what we do for NVIDIA backend for targeting these tensor cores on A100 and the newer generation of hardware is we use EMEA instructions from PTX. This is not so straightforward and as well as very bug prone. Similarly, the story is not so different with the AMD, where you have MFMA instructions for CDNA architectures, which are MI200s and 300s series. The question is, do we write such assembly level instructions and maintain it for a long time for these long and complex codes? And thankfully, we have a SYCL extension. When I say extension, this is not a specification. This is a new extension in DPC++ called Joint Matrix. So this extension provides certain set of APIs to give a really clean solution for portable matrix hardware programming model. And the last one is, how do we get better performance out of by doing optimizations? So we use DPC++ SYCL extension called eSIMD. These are really low level for just Intel GPUs. But of course, the limitation is, since these are written for Intel GPUs, we hope that this specification is extended to other vendors as well. In investigating the performance gap, we try to close the gap between SYCL and the native programming models by improving the compilers. So these are three set of features, simple tweaks that we did to get a good bit of performance and close the gap between SYCL and highly optimized native CUDA and HIP programming model. So we had issues with the PTX instructions being generated and as well as use of registers. So all these were solved with simple compiler tools. Coming to the actual performance, this is the performance on Frontier, which has AMD GPUs, and we ran it about like 1,000 nodes, which is about 12,000 GPUs. The performance here is about, the SYCL performance is about 93 to 98% of highly optimized HIP code. So SYCL is truly portable and performant at the same time. And this is just not a simple mini app. This is an end-to-end application running for several minutes. So in conclusion, SYCL specification has its open standard and its ecosystem of libraries that has improved considerably over time. And this brings us 3 Ps, which is performance, portability, and productivity metrics, which one can track in this diverse architecture landscape. And lastly, not least, the integration of ISO C++ standards into the SYCL specification has been really a game changer in evolving the standards. And that's pretty much. Thank you for your time.